problem 4, we have our slope field. And we haven't seen a slope field for a while on a free response, but it is still an essential concept. One of the things I like to tell my students when they're doing these slope fields is to actually write the number of the slope out by each of these points and then try and draw your lines. So over here, I'm doing 2 times the x-coordinate minus the y-coordinate, and at these points x is 0. So really it's just the opposite of the y value. So this is going to have a slope of 1, this is going to have a slope of -1, and this is going to have a slope of -2. Over here, when x equals 1, it's going to be 2 times 1 plus these. So it's basically going to be twice as high as these. So they're looking at a slope of 0, a slope of +1, and over here a slope of +3. The other thing that's important to know when we're dealing with slope fields is that it's not necessary that you draw something that's exactly a slope of 1 or exactly a slope of 3, but that there's a obvious, clear difference between those. So when I'm looking at a slope of 1, and I'm looking at a slope of 3, the 3 should be sizably steeper. This 1 over here should be about the same slope that this one was. And this -1 should be about the same angle, just going downhill instead of uphill. And this 2 should be steeper, again going downhill. A 0 slope should be a horizontal tangent line. And so our slope field should look something like this. Again, we're talking about relative slopes. We're not talking about absolute slopes. So it's important that certain slopes go downhill and certain slopes go uphill. It's important that steeper slopes be steeper. But in general, these have usually just been 1 point. So I'm not expecting anything more than a 1 point. It's basically going to be an all or nothing type thing on this problem. For parts 2 and 3, we're going to be dealing with this differential equation. So for part B, it says let d squared y over dx squared be in terms of x and y. Well, I know that what we're looking for is we're looking for the change with respect to x of dy dx. So I'm looking for the derivative of 2x minus y with respect to x. So for us, that's going to be 2 minus dy dx. And this would be fine, except they do tell us to put it in terms of x and y. So this is going to be 2 minus dy dx, which is this expression. So 2x minus y. And I'm going to distribute this negative because we're going to need it later. So it's going to be 2 minus 2x plus y. And so that's what our second derivative is equal to. And then they say to determine the concavity of all solutions for the given differential equation in quadrant 2. Well, when I'm looking at quadrant 2, I know that all the points here have a negative for x and a positive for y. So in quadrant 2, what happens is d squared y over dx squared ends up being 2 minus a negative number plus a positive number. So this is really 2 plus a positive, which is greater than 0. So d squared y over dx squared is greater than 0 because x is less than 0 and y is greater than 0. Therefore, we're concave up. And we're going to be concave up for all points in this quadrant because of this behavior, because my x's are negative, because my y's are positive. My second derivative is always going to be 2 plus the sum of positive numbers. So it's always going to be positive, and we're always going to end up being concave up. In part C, it says let y be f of x be a particular solution to the differential equation with the initial condition f of 2 equals 3. Do I have a relative minimum, maximum, or neither? And I need to look at the behavior of dy dx in order to know if we have a critical point or not. So dy dx at the point where x equals 2 and y equals 3 is equal to 2 times 2 minus 3, or 1. And that's not 0. So we're neither a max nor a min, because the derivative isn't a horizontal tangent line and it's not undefined. So because the derivative is equal to 1, which is not 0, we're neither a max or a min. And then finally, part D, it says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So This was part C. In part D, if I know that y equals mx plus b, then my derivative is just going to be m. But I know that my derivative is supposed to be 2x minus y. So I have this equation involving m, x, and y. And I know if I look at the second derivative of this function, I end up with a 0 because I have a constant slope. But I know that my second derivative is equal to this expression, this 2 minus 2x plus y. And so what I've got here is I've got a system of equations that I have to simplify. And if I try and solve this using elimination, if I eliminate my 2x's and eliminate my 2y's, all that's left on the right side is 2. On the left side, I've got m plus nothing, so I know that m equals 2. So I've got one of my variables. So I'm going to substitute back into this equation here. I'm going to say that 2 equals 2x minus y, and this looks an awful lot like a linear relationship, which is what I was trying to find. The only thing I don't have is I don't have my terms in the proper place, and so I don't know that b equals negative 2. And I think actually stating that b equals negative 2 is quite important because it does say to find the values of the constants m and b. So I think you actually will get a point for saying b equals negative 2, and I don't think this will be sufficient. You'll probably get a point for writing m equals 2. You'll get a point for finding the derivative and specifying that it's neither a max or a min. You're going to get a point for finding the second derivative in terms of x and y. You're going to get a point for concave up and a point for your justification. And then the other point that we're looking at is probably going to come from the slope field that we have up above. So that's what I'm looking